Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. As a part of our discussion on transition metal CH-H8 complexes, let me just recapitulate what we have been discussing in the previous lecture. We have been looking at CH-H8 ligand in the pretext of other common arene type ligands which are prevalent in organometallic chemistry, like cyclopentadienyl or C6H6 or C7H7, and building up on that we have started looking at CH-H8 ligands and its transition metal complexes. Now, as a part of our discussion in the last lecture, we have also observed that CH-H8 ligand can bind in two fashion. It can have a puckered non-planar structure in which CH-H8 more or less exhibits a butadiene type of structure, and the whole CH-H8 ring has 4 double bonds, as opposed to this puckered structure. There exist another structures where CH-H8 can act as a 10 electron planar and exhibit a planar structure and acts as a 10 electron donor, and in that form it is dianionic in nature. So, we had also looked into the preparations of the planar form of CH-H8 ligands with its transition metal complexes, and have also looked into various structurally characterized examples in which the transition metal have been found to bind to planar form of the CH-H8 ligand as well, and alongside also to the puckered form of the CH-H8 ligands. We had taken some examples, considered some examples in our previous discussion, and then coming into this class we are going to be discussing more on various kinds of complexes that CH-H8 ligand makes. So, the structural properties of CH-H8 ligand is discussed, is shown in the example below. So, a non-planar structure is observed when CH-H8 binds via mono, di or tri olefin, and this is illustrated in the example shown over here. This is bound by 1, 2, 3, 4, 5, 6, it has 6 fashion bound to molybdenum, which in turn is bound to 3 carbonyl, and the structure of the CH-H8 ligand is non-planar. And one can see the puckered structure of this complex. Similarly, in cod palladium dichloride, palladium this C8H8 link is also non-planar and tub like. So, what one sees is the fact that when this CH88 ligand binds via mono or di or tri olefins, then there is chances that there one obtained a pucker, one will obtain a pucker or non-planar structure. Another interesting aspect of these complexes are that some of these complexes are fluxional at room temperature. So, the fluxional properties of C8H8 complexes are illustrated in the examples given below. In particular, the reaction of FeCO5 plus C8H8 in octane at 125 degrees centigrade eliminates 2 COs to give this kind of complex where this cord ring is bound in at a 5 fashion to 3 CO molecules, and fluxionality is observed in eta 4 CHH unit in eta 4 C8 H8 unit. Adjacent double in bond in the coordinated sheaf undergoes rapid exchange. Double bond in coordinated eta 4 C8 H8 undergoes rapid exchange. That means, in solution even at minus 150 degree centigrade, only one signal is observed for eta 4 CH H8 unit. So, what does that mean is that these will exchange with the other CH H8 unit, and that there is these two things just keep on exchanging among itself. So, that at even at temperature above 180 degree centigrade, that one could see only one type of C4H8 eta bound C4H8 units. So, different binding properties of these CH88 ligand is explained here. For example, the bis CH C8H8 iron complex, which can be obtained by FeCl3 plus IC3H7 MgCl plus C8H8 in ether minus 30 degree centigrade gives FeC8H8 whole 2, whereas the same compound can also be prepared from a different precursor FeAC iron acetyl acetonate plus Al triethyl aluminum C2H5 whole 3 plus C8H8. This at minus 10 degree centigrade gives this compound. This compound has two different binding modes observed. These iron compounds contain two different binding modes. One is eta 6 C8H8 and eta 4 C8H8. So, eta 6 means that there is only the triolefin is only binding, and eta 4 means diolefin is binding, which sort of indicates that the ring definitely is not going to be a planar one, because only in eta 8 mode that a planar dianionic C4 C8H8 ligand is observed. So, this sort of gives an idea as to what are the structures. In one structure, the C8H8 is bound the way it is shown over here. If we so again the iron over here is in iron 0 state, and this is 18 electron compound. This is 1, 2, 3, 4, 5, 10 plus 8 is 18 valence electron compound. And if you see that this needs some kind of reducing agent, because the starting precursor is indeed iron 3 iron acetyl acetonate or FeCl3, which is also iron 3, but in the final compound it is iron 0. So, there some kind of reduction reagent, reducing reagent is required, and we see that this C8H8 complex does have two different kind of CH88 ring. One is bound in a eta 4 fashion, whereas the other one is bound in a eta 6 fashion, and two different binding. Also, as was seen for the other complex, at 25 this compound is fluxional, and at 25 degree centigrade only one signal of CH88 ligand is observed in proton and 13C NMRs. So, this is kind of interesting that these molecules are indeed non-planar, and as has been said earlier, that if mono, di, tri or tetraolefin just coordinates, then one is going to get non-planar structure, and this is exactly what is seen over here. Now, CHH8 can also act as a bridging ligand, and this is illustrated by the example shown over here. So, C8H8 as a bridging ligand. Now, these bridging ligands are commonly observed or the example that we are going to be talking about are observed for the bis CH88 complex of chromium and tungsten. So, before I go and talk about the structure of these two bis CH88 ligand of chromium and tungsten, which are isostructural, let me just give the synthesis of these two compounds, chromium here 2 CH88 whole 3 and tungsten 2 CH88 whole 3. The reactions are given over here before the structural discussion is initiated on these two dinuclear complexes. For chromium, the reaction of chromium trichloride plus 3 I C3 H7 Mg Br plus 3 C8 H8 in H nu and ether gives Cr2 C8 H8 whole 3. Similarly, one can do Cr chromium gas plus 2 C8 H8 gas, and by the co-condensation method minus 196 degree centigrade one would get this dichromium tris C8H8 ligand, and the correspondingly the tungsten compound however is prepared by a slightly different method in which it is directly reacted with the dianionic C8H8 ligand. So, WCl4 plus K2 C8H8 in presence of THF would give to W2 C8H8 whole thrice. Now, here CH8H and act as a bridging ligand between the two metal centers. So, the interesting thing about these two complexes is that C8H8 acts as a bridging ligand between two metal centers. Let me illustrate this fact with the structural characterization of these two complexes. The X-ray data, single crystal data indeed show that these are bridging systems of CH88 ligands. So, Cr2 C8H8 whole 3 and W2 C8H8 whole 3 contain bridging C8H8 ligands. So, let me just illustrate this with the example. And another these two unit is bound to two metals and which in turn are bound to this ring, another the third C8H8, and these are also bound to each other. So, there is a metal metal bond which is a chromium chromium bond, and that DCr Cr is 221 ppm picometer, and D tungsten is 237 picometer. So, here what we see is that there are two kinds of ligands. These is terminal C8H8, and this one is bridging C8H8. Okay. The terminal CHH8 are of eta 4 CHH8 type, and here also if this metal metal triple bond is observed, is considered, then it is 18 valence electron complex, and there is a fluxionality is observed in solution in proton NMR. Is observed in solution in proton NMR. So, these are highly dynamic systems which contains these dinuclear chromium chromium or tungsten tungsten complexes supported by both bridging and terminal C8H8 ligands. There is another bridging complex in which this C8H8 bridges between two nickel center, and this is illustrated by this nice example. So, we are going to bridging C8H8 in Ni2 CH8 whole 2 complex, and in this it is prepared by the reaction of complex of nickel plus C8H8 at minus 40 degree centigrade contains these ring, where these are bound in a these both the nickels are bound in a eta 3 fashion, and similarly over here so interesting thing is that both of the nickel center is bound in a eta 3 fashion, and the CHH8 ligand is acting as a bridging ligand supporting a dinuclear structure. So, both the nickel is eta 3 C8H8 allele type coordinated complex. So, with this I would like to conclude our discussion of C8H8 type of complexes. Particularly in this lecture, we have looked into this structure and reactivity of the CH-H8 type complexes, and what we had seen that the CH-H8 type complexes can bind in both the fashions bridging and terminal, and also it can show change in hapticity which can varies a lot. What we had observed is that a non-planar structure is obtained if it binds with monoolefin, diolefinic or triolefinic form, whereas if all the 8 carbon atoms are engaged to the transition metal, then it can bind in a planar form. Now, these molecules, apart from different binding, it can also another characteristic is the fact that it is they are also very fluxional, in the sense that at room temperatures higher than room temperature, or even temperatures which are even lower than room temperatures, these compounds show rapid exchange between the ligand and the metal center. Also, what is came to fore that they not only can form mononuclear complexes, but they also can exhibit dinuclear complexes, and in those cases this hapticity can vary from 3 to 5. So, apart from 2, 4, 6, 8 kind of activity, these complexes can also show activity hapticity of 3 and 5. So, with these we conclude our discussion on C8H8 ligands, complexes of transition metal, and these sort of close down on our discussions of various sigma donor pi acceptor kind of ligands, starting from allele and going up all the way to C5H5 to then C6H6, then following up on C7H7 and finishing with CH88. So, these are very nice set of ligands that we have looked in detail. We have tried to understand their bonding, particularly from the level of their molecular orbital, and get a glimpse of the electronic structure, which sort of can help us understand their reactivity. We have looked into various preparative methods available for preparing these complexes, and also we have looked into the structure and the reactivity repercussions that come out of these electronic structures that we have discussed. So, with that in backdrop, we are going to finish our topic on C8H8 ligand in this lecture, and then we are going to move on to the heterocycles. These are very interesting bits of compounds, and they also needs a good full-fledged discussion on their structure and reactivity, and which as well as their property, which will be taken up in the next lecture. So, with this I once again thank you for patiently listening to this lecture, and then look forward to taking up a new topic starting next lecture, where we are going to be talking about heterocyclic organometallic chemistry. So, till then, goodbye and thank you.